Here we're going to look at what are called the real zeros of a polynomial, and we're going to use those real zeros to graph polynomial functions. So let's say that you were given the following polynomial. P of x is equal to x squared plus 3x minus 10. So let's say we ask the question, when is the polynomial p of x equal to 0? So solutions to that equation, that is numbers that cause this to be true, that is cause the polynomial to be 0, they're called zeros. So zeros of a polynomial are such that p of c is equal to 0. So c is a 0 if it causes the polynomial. If you evaluate, if you plug it in and you get 0. Now it turns out that there are going to be, generally in our class, Precalculus Algebra, there are going to be both real and complex numbers, or numbers containing with an imaginary component that cause this to be true. So right now we're just going to say what happens if you have what are called real zeros, that is just real numbers that cause this to be true. So right now we're thinking about real zeros. So remember that, this question, when is the polynomial equal to 0? That's the same question we were asking in intermediate algebra when we were looking for x-intercepts. So if you have real zeros, then those zeros are also x-intercepts. And they're x-intercepts because when you go to find x-intercepts, that's what you do. You set the y-coordinate equal to 0 and you solve that equation. So if you find real zeros, that is solutions to this equation, those are also x-intercepts. So how would you do that for this polynomial? Well, how would you figure out when it's equal to 0? Well, just like from before, what you do is you'd factor, and you'd have p of x is equal to x plus 5 times x minus 2. And we see that the real zeros of this polynomial would be negative 5 and positive 2. That is, the real zeros are the values that cause each of these factors to be 0. So negative 5 and 2 are zeros. Well, actually, let's write real zeros. And therefore also x-intercepts. X-intercepts. Let's rewrite that. Okay, so those three things go hand in hand. Real zeros, x-intercepts, and x take away that number being a factor of the polynomial. So for example, 2 is a 0, and x take away 2 is a factor of this polynomial. So let's write that down. So generally, the following statements are logically equivalent. So generally, these are equivalent. And we're assuming here that c is a real number. We're going to have to deal with complex numbers in a little bit later. Well, I should say complex numbers with an imaginary part a little later. But generally, these three statements are equivalent. X take away c is a factor of p of x. That's equivalent to c is a 0 of p of x. And that's the same thing as saying c is an x-intercept of the graph of the polynomial. Okay. All right, so we're going to use these together with end behavior to graph polynomials, and there's one other thing we need to add to the mix, and let's go ahead and do that now. So we're going to factor, find the zeros, and graph. Okay, so the first thing you do is you factor, so it's going to be p of x is equal to 3x times x squared minus x minus 6. And this can be factored further, so p of x is equal to 3x times x minus 3 times x plus 2. So my zeros are 0, so you set the factors to 0, right? So I have one 0 when x is 0, I have another 0 when x is 3, and I have another 0 when x is negative 2. Those are numbers that cause each of these to be 0. So you create a number line with these three numbers in order on that number line. So it's going to be, let's see, negative 2, and then 0, and 3. And you want to leave a little space to the left of this number and to the right of that number because we're actually creating intervals. So here's the first interval, here's the second interval, and here the third interval and the fourth interval. And what we're doing is we're trying to figure out where the polynomial is positive and where it's negative. That is, we want to know the sign of the polynomial in these intervals. And notice that these zeros are successive zeros, right? -2, 0, 3. There's no zero in between these, for example. I found all my zeros right here. So what that means is that when you have successive real zeros, what that means is that the graph has to be completely above the x-axis or completely below the x-axis between the two zeros. For example, between -2 and 0, the y-coordinate has to either be completely positive or completely negative. That is, positive all over the whole interval or negative over the whole interval. And you might ask yourself why. Why can't the graph go like this? Why can't it be negative and then be positive? And the answer is because we have a polynomial, and a polynomial basically is continuous, which means that there's no hole or break. And what that means is that how would the polynomial go from being negative to being positive? Well, if it did, it would have to cross the x-axis. But we just said a moment ago that these are successive zeros, that there's no zero in between. And that means that if you know it's negative, it can't suddenly be positive in the same interval. It has to stay negative. And likewise, if it's positive here, it's got to stay positive. It can't cross again, okay? And that allows us to pick what are called test points in each of the respective intervals. In other words, if I pick like -3 and I plug it into the polynomial, whatever sign I get, positive or negative, that means that the polynomial has to remain positive or negative whenever x is less than -2. And likewise, I could pick a test point between -2 and 0, pick like the number -1 as a test point, and you can plug that into the polynomial, and that'll tell you if the polynomial is positive or negative, and it's got to remain positive or negative in that interval. Likewise, a test point between 0 and 3 would be 1. Beyond 3, a good test point would be 4. So let's plug those values into the polynomial and see what we get. So p of -3, you plug that into the original polynomial. So it's going to be 3 times, and you could also plug it into the factored form if you want. Either way, but let's plug it into the original polynomial. So 3 times -3 cubed minus 3 times -3 squared minus 18 times -3, and we end up getting, when all is said and done, we get the number, what's that going to be? -54. Okay, now what that means is that, if you plug in -3, you get a negative number. So I'm going to put a negative here indicating that the polynomial is negative whenever x is less than -2. Because a test point is an indicator of the sign over the entire interval. Let's go to our next test point, -1. So p of -1, when you do the same thing and you plug it in, you're going to get positive 12. Okay, and it's positive, so I'm going to put a positive sign right there, meaning the graph is completely above the x-axis between -2 and 0. My third test point is going to be 1. And when I plug that in, just like before, I get -18. And then finally I plug in 4. And when I do so, I get positive 72. Okay, so let's go ahead and, well, first of all, for the test point 1, it was negative, right? So when I plugged in that test point, I got a negative. And when I plugged in the test point over here, 4, I ended up getting positive 72. So I write positive. So first thing, let's go ahead and plot the points we have. So we have intercepts at 0, 3, and -2. So we have an intercept at -2. We have an intercept at 0 and an intercept at 3. And notice that I scaled the y-axis beforehand because I knew I was going to get large numbers for my test points. So generally you create test points and then you have to scale the y-axis. So I did that beforehand, but that's generally how you're going to do it. You're going to pick test points and then you're going to scale the y-axis. And the reason is because these test points not only give you the sign, but they're also points on your graph, right? Because if you plug in -3 into the polynomial, you get out -54. So when x is -3, y is -54. So it's way down here. It's going to be like maybe there, -54 or so. When you plug in -1, you get positive 12. So -1 positive 12 is going to be maybe right there. When I plug in positive 1, I get negative 18. So right here, maybe? So I've got that point on the graph. Let's see if I can draw that a little bigger. Got this point. Okay, and finally I have, when I plug in 4, I get 72. Way up here. It's maybe like right there or so. Okay, so generally I can see what's happening, right? The graph is negative down here. It comes up, it hits 0. It's positive between negative 2 and 0. And then it's going to be negative between 0 and when x is between 0 and 3. And then the y-coordinate is going to be positive when x gets large. Now think about also the end behavior of the graph. From a previous video, we know that whenever the exponent is, whenever the leading term has an odd exponent and a positive lead coefficient, that means as x goes to infinity, y goes to infinity. And as x goes to negative infinity, y goes to negative infinity. So this behavior looks right. It's going down like that, it's going up, going down, and then it's going up like that. Okay? So let's go ahead and put that all together and create a graph here. Okay, so this would be a reasonable graph of this polynomial based on that information. Now notice that there are still some points that we haven't yet considered, and one point being, where is that top? Where is the local maximum here? Even though I graphed this point there, you don't know. The graph may have actually gone up and then come back down. So you have to be kind of careful because we don't yet have all the information. We have quite a bit of information, but we still are looking for places where you have local maximums and local minimums. And we're going to need techniques from calculus to be able to do that accurately. Notice that I put arrows on here indicating the end behavior, right? Going to infinity and going to negative infinity. Okay, let's try another one like that. Let's find the zeros of this polynomial and graph it. So the first step is to factor. So we have p of x is equal to, well, let's just write the polynomial negative x to the fourth minus x cubed plus 2x squared. And let's factor out it's going to be a negative x squared. That's our GCF. And then we have that times x squared. It's going to be plus x, and then minus 2. That can be factored further, so p of x is equal to negative x squared, and we have x plus 2 times x minus 1. So I've got my zeros. 0 is a 0, negative 2 is a 0, and 1 is another 0, and these are all x-intercepts as well. So we write those, or put those on a number line in order. So negative 2, 0, and 1, and pick test points. So negative 3, negative 1, 1/2, and 2. You just want simple points in each of the intervals. You evaluate the polynomial at those values. So p of negative 3, when you plug that in, you're going to get negative 36. P of negative 1, when you plug that in, you're going to get positive 2. When you plug in 1/2, you are going to get 5/16. And when you plug in finally the last test point of 2, you're going to get negative 16. So p of negative 3, it's negative, so the graph is negative there. P of negative 1 is a positive. P of 1/2 is a positive as well. And p of 2 is a negative. Notice that usually a lot of times polynomials change signs at zeros, so from negative to positive. At this 0, there was no change of sign. That's an interesting behavior that we'll see later on. So polynomials do not always change sign at zeros. So let's plot our graph our x-intercept. So we have one at negative 2, we have one at 0, we have one at 1. Let's make those big. And then we also have these points. P of negative 3, whoops, let's extend this graph a little bit. So P of negative 3, that's equal to negative 36. So it comes down here, so maybe like right, I'd say there. P of negative 1 is positive 2, so maybe right here. P of 1/2 is 5/16. So really small, right? P of 1/2 is 5/16, really tiny. and then p of 2 is negative, I gotta put another one in there, yikes. So p of 2 gives what? Negative 16. Okay, so what's our graph basically doing? Well, it's negative, comes up, and then it's positive, and then it's 0 here, but it's positive there as well, and then it comes back down, and then it's going like that. And we can see that the n-like behavior, or the n behavior rather, because it's an even exponent and a negative coefficient, what that means is that as x goes to infinity, y goes to negative infinity, and as x goes to negative infinity, y goes to negative infinity as well. So when we graph a polynomial through those points, here's what we're going to get. Okay, so this would be a graph of that polynomial. And notice that it comes up, it's positive, and it's smooth right there. There's no kink or corner. Polynomials never have kinks or corners. It's a smooth graph right there. And then it comes up again, and then it goes to negative infinity. So generally, like I was saying, there's more to do with graphing, and we're going to have some ways of finding these maximums and minimums in calculus. But this is a good first base for graphing. Okay, until next time.